Welcome to the I Can't Sleep podcast, where I read random articles from across the web to bore you to sleep with my soothing voice. I'm your host, Benjamin Boster. Today's episode is from a Wikipedia article titled Astrophysics. Astrophysics is a science that employs the methods and principles of physics and chemistry in the industry of astronomical objects and phenomena. As one of the founders of the discipline, James Keeler, said, astrophysics seeks to ascertain the nature of the heavenly bodies, rather than their positions or motions in space, what they are, rather than where they are. Among the subjects studied are the Sun, other stars, galaxies, extrasolar planets, the interstellar medium, and the cosmic microwave background. Emissions from these objects are examined across all parts of the electromagnetic spectrum, and the properties examined include luminosity, density, temperature, and chemical composition. Because astrophysics is a very broad subject, astrophysicists apply concepts and methods from many disciplines of physics, including classical mechanics, electromagnetism, statistical mechanics, thermodynamics, quantum mechanics, relativity, nuclear and particle physics, and atomic and molecular physics. In practice, modern astronomical research often involves a substantial amount of work in the realms of theoretical and observational physics. Some areas of study for astrophysicists include their attempts to determine the properties of dark matter, dark energy, black holes, and other celestial bodies, and the origin and ultimate fate of the universe. Topics also studied by theoretical astrophysicists include solar system formation and evolution, stellar dynamics and evolution, galaxy formation and evolution, magnetohydrodynamics, large-scale structure of matter in the universe, origin of cosmic rays, general relativity, special relativity, quantum and physical cosmology, including string cosmology and astroparticle physics. History. Astronomy is an ancient science, long separated from the study of terrestrial physics. In the Aristotelian worldview, bodies in the sky appeared to be unchanging spheres, whose only motion was uniform motion in a circle, while the earthly world was the realm which underwent growth and decay, and in which natural motion was in a straight line, and ended when the moving object reached its goal. Consequently, it was held that the celestial region was made of a fundamentally different kind of matter from that found in the terrestrial sphere, either fire as maintained by Plato, or aether as maintained by Aristotle. During the 17th century, natural philosophers such as Galileo, Descartes, and Newton began to maintain that the celestial and terrestrial regions were made of similar kinds of material, and were subject to the same natural laws. The challenge was that the tools had not yet been invented with which to prove these assertions. For much of the 19th century, astronomical research was focused on the routine work of measuring the positions and computing the motions of astronomical objects. A new astronomy, soon to be called astrophysics, began to emerge when William Hyde Wollaston and Joseph von Fraunhofer independently discovered that, when decomposing the light from the sun, a multitude of dark lines, regions where there was less or no light, were observed in the spectrum. By 1860, the physicist Gustav Kirchhoff and the chemist Robert Bunsen had demonstrated that the dark lines in the solar spectrum corresponded to bright lines in the spectra of known gases, specific lines corresponding to unique chemical elements. Kirchhoff deduced that the dark lines in the solar spectrum are caused by absorption by chemical elements in the solar atmosphere. In this way, it was proved that the chemical elements found in the sun and stars were also found on Earth. Among those who extended the study of solar and stellar spectra was Norman Lockyer, who in 1868 detected radiant as well as dark lines in solar spectra. Working with chemist Edward Franklin to investigate the spectra of elements at various temperatures and pressures, he could not associate a yellow line in the solar spectrum with any known elements. He thus claimed the line represented a new element, which was called helium, after the Greek Helios, the sun personified. In 1885, Edward C. Pickering undertook an ambitious program of stellar spectral classification at Harvard College Observatory, in which a team of women computers, notably Williamina Fleming, Antonia Maury, and Annie Jump Cannon, classified the spectra recorded on photographic plates. By 1890, a catalog of over 10,000 stars had been prepared that grouped them into 13 spectral types. Following Pickering's vision, by 1924, Cannon expanded the catalog to 9 volumes and over 250,000 stars, developing the Harvard classification scheme, which was accepted for worldwide use in 1922. In 1895, George Ellery Hale and James E. Keeler, along with a group of 10 associate editors from Europe and the United States, established the Astrophysical Journal, an international review of spectroscopy and astronomical physics. It was intended that the journal would fill the gap between journals in astronomy and physics, providing a venue for publication of articles on astronomical applications of the spectroscope, on laboratory research closely allied to astronomical physics, including wavelength determinations of metallic and gaseous spectra, and experiments on radiation and absorption, on theories of the sun, moon, planets, comets, meteors, and nebulae, and on instrumentation for telescopes and laboratories. Around 1920, following the discovery of the Hertzsprung-Russell diagram, still used as the basis for classifying stars and their evolution, Arthur Eddington anticipated the discovery and mechanism of nuclear fusion processes in stars in his paper, The International Constitution of the Stars. At that time, the source of stellar energy was a complete mystery. Eddington correctly speculated that the source was fusion of hydrogen into helium, liberating enormous energy according to Einstein's equation, E equals mc squared. This was a particularly remarkable development since at that time, fusion and thermonuclear energy, and even that stars are largely composed of hydrogen, had not yet been discovered. In 1925, Cecilia Helena Payne, later Cecilia Payne-Gaposchkin, wrote an influential doctoral dissertation at Radcliffe College, in which she applied ionization theory to stellar atmospheres to relate the spectral classes to the temperature of stars. Most significantly, she discovered that hydrogen and helium were the principal components of stars. Despite Eddington's suggestion, this discovery was so unexpected that her dissertation readers convinced her to modify the conclusion before publication. However, later research confirmed her discovery. By the end of the 20th century, studies of astronomical spectra had expanded to cover wavelengths extending from radio waves through optical, X-ray, and gamma wavelengths. In the 21st century, it further expanded to include observations based on gravitational waves. Observational astrophysics. Observational astronomy is a division of the astronomical science that is concerned with recording and interpreting data, in contrast with theoretical astrophysics, which is mainly concerned with finding out the measurable implications of physical models. It is the practice of observing celestial objects by using telescopes and other astronomical apparatus. The majority of astrophysical observations are made using the electromagnetic spectrum. Radio astronomy studies radiation with a wavelength greater than a few millimeters. Example areas of study are radio waves, usually emitted by cold objects such as interstellar gas and dust clouds. The cosmic microwave background radiation, which is the redshift light from the Big Bang. Pulsars, which were first detected at microwave frequencies. The study of these waves requires very large radio telescopes. Infrared astronomy studies radiation with a wavelength that is too long to be visible to the naked eye, but is shorter than radio waves. Infrared observations are usually made with telescopes similar to the familiar optical telescopes. Objects colder than stars, such as planets, are normally studied at infrared frequencies. Optical astronomy was the earliest kind of astronomy. Telescopes paired with a charge-coupled device or spectroscopes are the most common instruments used. The Earth's atmosphere interferes somewhat with optical observations, so adaptive optics and space telescopes are used to obtain the highest possible image quality. In this wavelength range, stars are highly visible, and many chemical spectra can be observed to study the chemical composition of stars, galaxies, and nebulae. Ultraviolet, X-ray, and gamma-ray astronomy study very energetic processes such as binary pulsars, black holes, magnetars, and many others. These kinds of radiation do not penetrate the Earth's atmosphere well. There are two methods in use to observe this part of the electromagnetic spectrum: space-based telescopes and ground-based imaging air Cherenkov telescopes, IACT. Examples of observatories of the first type are RXTE, the Chandra X-ray Observatory, and the Compton Gamma Ray Observatory. Examples of the IACTs are the High Energy Stereoscopic System, HESS, and the MAGIC telescope. Other than electromagnetic radiation, few things may be observed from the Earth that originate from great distances. A few gravitational wave observatories have been constructed, but gravitational waves are extremely difficult to detect. Neutrino observatories have also been built, primarily to study the Sun. Cosmic rays consisting of very high-energy particles can be observed hitting the Earth's atmosphere. Observations can also vary in their timescale. Most optical observations take minutes to hours, so phenomena that change faster than this cannot readily be observed. However, historical data on some objects is available, spanning centuries or millennia. On the other hand, radio observations may look at events on a millisecond timescale or combine years of data. The information obtained from these different timescales is very different. The study of the Sun has a special place in observational astrophysics. Due to the tremendous distance of all other stars, the Sun can be observed in a kind of detail unparalleled by any other star. Understanding the Sun serves as a guide to understanding of other stars. The topic of how stars change, or stellar evolution, is often modeled by placing the varieties of star types in their respective positions on the Hertzsprung-Russell diagram, which can be viewed as representing the state of a stellar object from birth to destruction. Theoretical astrophysics. Theoretical astrophysicists use a wide variety of tools, which include analytical models, for example, prototypes to approximate the behaviors of a star, and computational numerical simulations. Each has some advantages. Analytical models of a process are generally better for giving insight into the heart of what is going on. Numerical models can reveal the existence of phenomena and effects that would otherwise not be seen. Theorists in astrophysics endeavor to create theoretical models and figure out the observational consequences of those models. This helps allow observers to look for data that can refute a model or help in choosing between several alternate or conflicting models. Theorists also try to generate or modify models to take into account new data. In the case of an inconsistency, the general tendency is to try to make minimal modifications to the model to fit the data. In some cases, a large amount of inconsistent data over time may lead to total abandonment of a model. Topics studied by theoretical astrophysicists include stellar dynamics and evolution, galaxy formation and evolution, magnetohydrodynamics, large-scale structure of matter in the universe, origin of cosmic rays, general relativity and physical cosmology, including string cosmology and astroparticle physics. Relativistic astrophysics serves as a tool to gauge the properties of large-scale structures for which gravitation plays a significant role in physical phenomena investigated, and as the basis for black hole astrophysics and the study of gravitational waves. Some widely accepted and studied theories and models in astrophysics now included in the lambda CDM model are the Big Bang, cosmic inflation, dark matter, dark energy, and fundamental theories of physics. Popularization. The roots of astrophysics can be found in the 17th century emergence of a unified physics, in which the same laws applied to the celestial and terrestrial realms. There were scientists who were qualified in both physics and astronomy who laid the firm foundation for the current science of astrophysics. In modern times, students continued to be drawn to astrophysics due to its popularization by the Royal Astronomical Society and notable educators such as prominent professors Lawrence Krauss, Subramaniam Chandrasekhar, Stephen Hawking, Hubert Reeves, Carl Sagan, Neil deGrasse Tyson, and Patrick Moore. The efforts of the early, late, and present scientists continue to attract young people to study the history and science of astrophysics. The television sitcom show The Big Bang Theory popularized the field of astrophysics with the general public and featured some well-known scientists like Stephen Hawking and Neil deGrasse Tyson. Astronomical spectroscopy. Astronomical spectroscopy is the study of astronomy using the techniques of spectroscopy to measure the spectrum of electromagnetic radiation, including visible light, ultraviolet, X-ray, infrared, and radio waves that radiate from stars and other celestial objects. A stellar spectrum can reveal many properties of stars such as their chemical composition, temperature, density, mass, distance, and luminosity. Spectroscopy can show the velocity of motion towards or away from the observer by measuring the Doppler shift. Spectroscopy is also used to study the physical properties of many other types of celestial objects, such as planets, nebulae, galaxies, and active galactic nuclei. Background. Astronomical spectroscopy is used to measure three major bands of radiation in the electromagnetic spectrum: visible light, radio waves, and X-rays. While all spectroscopy looks at specific bands of the spectrum, different methods are required to acquire the signal depending on the frequency. Ozone, O3, and molecular oxygen, O2, absorb light with wavelengths under 300 nanometers, meaning that X-ray and ultraviolet spectroscopy require the use of a satellite telescope or rocket-mounted detectors. Radio signals have much longer wavelengths than optical signals and require the use of antennas or radio dishes. Infrared light is absorbed by atmospheric water and carbon dioxide, so while the equipment is similar to that used in optical spectroscopy, satellites are required to record much of the infrared spectrum. Optical spectroscopy. Physicists have been looking at the solar spectrum since Isaac Newton first used a simple prism to observe the refractive properties of light. In the early 1800s, Joseph von Fraunhofer used his skills as a glassmaker to create very pure prisms, which allowed him to observe 574 dark lines in a seemingly continuous spectrum. Soon after this, he combined telescope and prism to observe the spectrum of Venus, the Moon, Mars, and various stars such as Betelgeuse. His company continued to manufacture and sell high-quality refracting telescopes based on his original designs until its closure in 1884. The resolution of a prism is limited by its size. A larger prism will provide a more detailed spectrum, but the increase in mass makes it unsuitable for highly detailed work. This issue was resolved in the early 1900s with the development of high-quality reflection gratings by J.S. Plaskett and the Dominion Observatory in Ottawa, Canada. Light striking a mirror will reflect at the same angle. However, a small portion of the light will be refracted at a different angle. This is dependent upon the indices of refraction of the materials and the wavelengths of the light. By creating a blazed grating, which utilizes a large number of parallel mirrors, the small portion of light can be focused and visualized. These new spectroscopes were more detailed than a prism, required less light, and could be focused on a specific region of the spectrum by tilting the grating. The limitation to a blazing grating is the width of the mirrors, which can only be ground a finite amount before focus is lost. The maximum is around 1,000 lines per millimeter. In order to overcome this limitation, holographic gratings were developed. Volume phase holographic gratings use a thin film of dichromated gelatin on a glass surface, which is subsequently exposed to a wave pattern created by an interferometer. This wave pattern sets up a reflection pattern similar to the blazed gratings, but utilizing Bragg diffraction, a process where the angle of reflection is dependent on the arrangement of the atoms in the gelatin. The holographic gratings can have up to 6,000 lines per millimeter and can be up to twice as efficient in collecting light as blazed gratings. Because they are sealed between two sheets of glass, the holographic gratings are very versatile, potentially lasting decades before needing replacement. Light dispersed by the grating or prism in a spectrograph can be recorded by a detector. Historically, photographic plates were widely used to record spectra until electronic detectors were developed, and today optical spectrographs most often employ charge-coupled devices, CCDs. The wavelength scale of a spectrum can be calibrated by observing the spectrum of emission lines of known wavelengths from a gas discharge lamp. The flux scale of a spectrum can be calibrated as a function of wavelength by comparison with an observation of a standard star, with corrections for atmospheric absorption of light. This is known as spectrophotometry. Radio spectroscopy. Radio astronomy was founded with the work of Carl Jansky in the early 1930s while working for Bell Labs. He built a radio antenna to look at potential sources of interference for transatlantic radio transmissions. One of the sources of noise discovered came not from Earth, but from the center of the Milky Way in the constellation Sagittarius. In 1942, J.S. Hay captured the sun's radio frequency using military radar receivers. Radio spectroscopy started with the discovery of the 21 centimeter HI line in 1951. Radio interferometry. Radio interferometry was pioneered in 1946 when Joseph Lade Pawsey, Ruby Payne Scott, and Lindsay McCready used a single antenna atop a sea cliff to observe 200 megahertz solar radiation. Two incident beams, one directly from the sun and the other reflected from the sea surface, generated the necessary interference. The first multi-receiver interferometer was built in the same year by Martin Riley and von Berg. In 1960, Riley and Antony Hewish published their technique of aperture synthesis to analyze interferometer data. The aperture synthesis process, which involves autocorrelating and discrete Fourier transforming the incoming signal, recovers both the spatial and frequency variation in flux. The result is a 3D image whose third axis is frequency. For this work, Riley and Hewish were jointly awarded the 1974 Nobel Prize in Physics. X-ray spectroscopy. Stars and their properties. Chemical properties. Newton used a prism to split white light into a spectrum of color, and Fraunhofer's high-quality prisms allowed scientists to see dark lines of an unknown origin. In the 1850s, Gustav Kirchhoff and Robert Bunsen described the phenomena behind these dark lines. Hot, solid objects produce light with a continuous spectrum. Hot gases emit light at specific wavelengths, and hot, solid objects surrounded by cooler gases show a near-continuous spectrum, with dark lines corresponding to the emission lines of the gases. By comparing the absorption lines of the sun with emission spectra of known gases, the chemical composition of stars can be determined. Not all of the elements in the sun were immediately identified. Two examples are listed below. In 1868, Norman Lockyer and Pierre Janssen independently observed a line next to the sodium doublet, which Lockyer determined to be a new element. He named it helium, but it wasn't until 1895 the element was found on Earth. In 1869, the astronomers Charles Augustus Young and William Harkness independently observed a novel green emission line in the sun's corona during an eclipse. This new element was incorrectly named coronium, as it was only found in the corona. It was not until the 1930s that Walter Groschrin and Bengt Edlund discovered that the spectral line at 530.3 nanometers was due to highly ionized iron. Other unusual lines in the coronal spectrum are also caused by highly charged ions, such as nickel and calcium, the high ionization being due to the extreme temperature of the solar corona. To date, more than 20,000 absorption lines have been listed for the sun between 293.5 and 877 nanometers. Yet only approximately 75% of these lines have been linked to elemental absorption. By analyzing the equivalent widths of each spectral line in an emission spectrum, both the elements present in a star and their relative abundances can be determined. Using this information, stars can be categorized into stellar populations. Population 1 stars are the youngest stars and have the highest metal content. The Sun is a population 1 star, while population 3 stars are the oldest stars with a very low metal content. Galaxies. The spectra of galaxies look similar to stellar spectra, as they consist of the combined light of billions of stars. Doppler shift studies of galaxy clusters by Fritz Zwicky in 1937 found that the galaxies in a cluster were moving much faster than seemed to be possible from the mass of the cluster inferred from the visible light. Zwicky hypothesized that there must be a great deal of non-luminous matter in the galaxy clusters, which became known as dark matter. Since his discovery, astronomers have determined that a large portion of galaxies and most of the universe is made up of dark matter. In 2003, however, 4 galaxies were found to have little to no dark matter influencing the motion of the stars contained within them. The reason behind the lack of dark matter is unknown. In the 1950s, strong radio sources were found to be associated with very dim, very red objects. When the first spectrum of one of these objects was taken, there were absorption lines at wavelengths where none were expected. It was soon realized that what was observed was a normal galactic spectrum, but highly redshifted. These were named quasi-stellar radio sources, or quasars, by Hong-Yi Chu in 1964. Quasars are now thought to be galaxies formed in the early years of our universe, with their extreme energy output powered by supermassive black holes. The properties of a galaxy can also be determined by analyzing the stars found within them. NGC 4550, a galaxy in the Virgo cluster, has a large portion of its stars rotating in the opposite direction as the other portion. It is believed that the galaxy is the combination of 2 smaller galaxies that were rotating in opposite directions to each other. Bright stars and galaxies can also help determine the distance to a galaxy, which may be a more accurate method than parallax or standard candles. Interstellar medium. The interstellar medium is matter that occupies the space between star systems in a galaxy. 99% of this matter is gaseous, hydrogen, helium, and smaller quantities of other ionized elements such as oxygen. The other 1% is dust particles, thought to be mainly graphite, stalactites, and ices. Clouds of the dust and gas are referred to as nebulae. There are 3 main types of nebula: absorption, reflection, and emission nebulae. Absorption, or dark nebulae, are made of dust and gas in such quantities that they obscure the starlight behind them, making photometry difficult. Reflection nebulae, as their name suggests, reflect the light of nearby stars. Their spectra are the same as the stars surrounding them, though the light is bluer. Shorter wavelengths scatter better than longer wavelengths. Emission nebulae emit light at specific wavelengths depending on their chemical composition. Gaseous emission nebulae. In the early years of astronomical spectroscopy, scientists were puzzled by the spectrum of gaseous nebulae. In 1864, William Huggins noticed that many nebulae showed only emission lines rather than a full spectrum like stars. From the work of Kirchhoff, he concluded that nebulae must contain enormous masses of luminous gas or vapor. However, there were several emission lines that could not be linked to any terrestrial element, brightest among them lines at 495.9 nanometers and 500.7 nanometers. These lines were attributed to a new element, nebulium, until Ira Bowen determined in 1927 that the emission lines were from highly ionized oxygen. These emission lines could not be replicated in a laboratory because they are forbidden lines. The low density of a nebula, 1 atom per cubic centimeter, allows for metastable ions to decay via forbidden line emission rather than collisions with other atoms. Not all emission nebulae are found around or near stars where solar heating causes ionization. The majority of gaseous emission nebulae are formed of neutral hydrogen. In the ground state, neutral hydrogen has two possible spin states. The electron has either the same spin or the opposite spin of the proton. When the atom transitions between these two states, it releases an emission or absorption line of 21 centimeters. This line is within the radio range and allows for very precise measurements. Velocity of the cloud can be measured via Doppler shift. The intensity of the 21 centimeter line gives the density and number of atoms in the cloud. The temperature of the cloud can be calculated. Using this information, the shape of the Milky Way has been determined to be a spiral galaxy, though the exact number and position of the spiral arms is the subject of ongoing research. Complex molecules. Dust and molecules in the interstellar medium not only obscure photometry, but also causes absorption lines in spectroscopy. Their spectral features are generated by transitions of component electrons between different energy levels, or by rotational or vibrational spectra. Detection usually occurs in radio, microwave, or infrared portions of the spectrum. The chemical reactions that form these molecules can happen in cold, diffuse clouds, or in dense regions illuminated with ultraviolet light. Most known compounds in space are organic, ranging from small molecules, e.g. acetylene and acetone, to entire classes of large molecules, e.g. fullerenes and polycyclic aromatic hydrocarbons, to solids such as graphite or other sooty material. Motion in the universe. Stars and interstellar gas are bound by gravity to form galaxies, and groups of galaxies can be bound by gravity in galaxy clusters. With the exception of stars in the Milky Way and the galaxies of the local group, almost all galaxies are moving away from Earth due to the expansion of the universe. Doppler effect and redshift. The motion of stellar objects can be determined by looking at their spectrum. Because of the Doppler effect, objects moving towards someone are blue shifted, and objects moving away are red shifted. The wavelength of redshifted light is longer, appearing redder than the source. Conversely, the wavelength of blue shifted light is shorter, appearing bluer than the source light. Peculiar motion. Objects that are gravitationally bound will rotate around a common center of mass. For stellar bodies, this motion is known as peculiar velocity and can alter the Hubble flow. Thus, an extra term for the peculiar motion needs to be added to Hubble's law. This motion can cause confusion when looking at a solar or galactic spectrum, because the expected redshift based on the simple Hubble law will be obscured by the peculiar motion. For example, the shape and size of the Virgo cluster has been a matter of great scientific scrutiny due to the very large peculiar velocities of the galaxies in the cluster. Binary stars. Just as planets can be gravitationally bound to stars, pairs of stars can orbit each other. Some binary stars are visual binaries, meaning they can be observed orbiting each other through a telescope. Some binary stars, however, are too close together to be resolved. These two stars, when viewed through a spectrometer, will show a composite spectrum. The spectrum of each star will be added together. This composite spectrum becomes easier to detect when the stars are of similar luminosity and of different spectral classes. Spectroscopic binaries can be also detected due to their radial velocity. As they orbit around each other, one star may be moving towards the Earth, whilst the other moves away, causing a Doppler shift in the composite spectrum. The orbital plane of the system determines the magnitude of the observed shift. If the observer is looking perpendicular to the orbital plane, there will be no observed radial velocity. For example, a person looking at a carousel from the side will see the animals moving toward and away from them, whereas if they look from directly above, they will only be moving in the horizontal plane. Planets, asteroids, and comets. Planets, asteroids, and comets all reflect light from their parent stars and emit their own light. For cooler objects, including solar system planets and asteroids, most of the emission is at infrared wavelengths we cannot see, but that are routinely measured with spectrometers. For objects surrounded by gas, such as comets and planets with atmospheres, further emission and absorption happens at specific wavelengths in the gas, imprinting the spectrum of the gas on that of the solid object. In the case of worlds with thick atmospheres or complete cloud cover, such as the gas giants Venus and Saturn's satellite Titan, the spectrum is mostly or completely due to the atmosphere alone. Planets. The reflected light of a planet contains absorption bands due to minerals in the rocks present for rocky bodies, or due to the elements and molecules present in the atmosphere. To date, over 3,500 exoplanets have been discovered. These include so-called hot Jupiters, as well as Earth-like planets. Using spectroscopy, compounds such as alkali metals, water vapor, carbon monoxide, carbon dioxide, and methane have all been discovered. Asteroids. Asteroids can be classified into three major types according to their spectra. The original categories were created by Clark R. Chapman, David Morrison, and Ben Zellner in 1975, and further expanded by David J. Tholen in 1984. In what is now known as the Tholen classification, the C-types are made of carbonaceous material, S-types consist mainly of silicates, and X-types are metallic. These are all classifications for universal asteroids. C and S-type asteroids are the most common asteroids. In 2002, the Tholen classification was further evolved into the SMASS classification, expanding the number of categories from 14 to 26 to account for more precise spectroscopic analysis of the asteroids. Comets. The spectra of comets consist of a reflected solar spectrum from the dusty clouds surrounding the comet, as well as emission lines from gaseous atoms and molecules excited to fluorescence by sunlight and/or chemical reactions. For example, the chemical composition of comet ISON was determined by spectroscopy due to the prominent emission lines of cyanogen, Cn, as well as 2 and 3 carbon atoms, C2 and C3. Nearby comets can even be seen in X-ray as solar wind ions fly into the coma are neutralized. The cometary X-ray spectra therefore reflect the state of the solar wind rather than that of the comet.